Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to begin our conversation on acids and bases. So these are some systems you're probably relatively familiar with, but let's go ahead and overview some of the big definitions. So one of the big things is when we're looking at acids and bases, they always tend to end up occurring together. For acids, you typically think about these as big, scary movie things, but you're actually interacting with acids on a daily basis, and your body's well developed in detecting whether an acid is present. Generally, if something tastes sour, it's probably an acid. Ta-da! That's the quickest way to determine an acidic solution. However, since you're not supposed to taste everything in a lab, there's also other things you can use like litmus paper, which will tend to turn red in the presence of an acid. So in terms of actually what's happening on a molecular level, one of the first people to describe this was Arrhenius, who is a Swedish scientist who also had to his name in 1896, published the first paper on climate change, where he proposed that humans pump CO2 into the atmosphere to produce a greenhouse effect. Yes, we are currently celebrating about 100 and almost 20 years now of climate change. It ain't new, it ain't controversial. However, one of his things that he's more well known for is the fact he also provided a definition of what an acid is. So, an acid is something that essentially, when you place it in water, will produce a hydrogen ion, also known as a proton and an anion. That's really what it is. And so you have things like hydrochloric acid, which produces a proton and chloride. You have acetic acid, which produces a proton and acetate. So again, we've seen this earlier in the semester. But one of the things I also want to emphasize is if these two examples look relatively familiar, it's because we also use these when talking about electrolytes, because it turns out under this Arrhenius definition, acids are just a form of electrolytes. So just like a strong electrolyte means you have complete dissociation, same thing with a strong acid. So if I have an acid that's also a strong electrolyte, that means it completely dissociates to produce an equal amount of protons as I originally added acids. So any acid that completely dissociates or is a strong electrolyte, we're also going to call a strong acid, which again makes sense. That's where the strong in strong acid comes from. So there are 7 major strong acids. The first 3 that are easy to remember are halides: hydrogen chloride, hydrogen bromide, and hydrogen iodide. They do not include hydrogen fluoride. That, with its slightly less ability to exist as a separate ion, not quite as soluble, means it's not so good at dissociation. However, our other 3 halides make perfectly good strong acids. The other 4 are our oxyacids, and we've seen these a fair amount: nitric acid, sulfuric acid, chloric acid, and perchloric acid. So all 7 of these you put in water, completely dissociate, making chloride, bromide, iodide, nitrate, sulfate, chlorate, and perchlorate. Every other acid that you interact with, we're going to typically treat as a weak acid. So it only is going to partially dissociate. However, in contrast, we can look at bases. So bases, our body is also very well developed at detecting, because almost any base will taste bitter. And actually, one of the reasons why we have an aversion to bitter compounds is it turns out that in nature, many bases exist as poisons. Most famously, the alkaloids, which are plant products that are quite toxic. Also, it is worth noting that bases can turn skin slippery, and one of the ways they do this is by reacting with the oils on your skin to make soap. This is commonly known as saponification. However, the Arrhenius definition of bases is actually kind of cool. So according to Arrhenius, a base is something that dissociates to produce hydroxide. If I have a strong base, that means it completely dissociates in the presence of water. So if we go ahead and look at our solubility table, we probably won't be that surprised to see that amongst our strong bases are alkali hydroxides, because again, lithium, sodium, potassium completely dissociate in the presence of water. However, we also have several others that aren't quite exactly perfectly soluble, but still form strong bases. That includes things like magnesium, calcium, strontium, and barium. It is worth noting that while these are only slightly soluble, one of the reasons why they're classified as strong acids is because if you have any acid, or strong bases, is if you have any acid present in solution, all 9 of these bases will completely react with that acid. So again, while they might not dissociate perfectly in water, they will completely react with any acid present. Which brings us to the important idea of, well, how do acids and bases react? So if you put an acid and a base together, they perform what's called a neutralization reaction. So this typically produces a salt and water. Again, according to our Arrhenius definition. And we can go ahead and look at this by looking at a strong acid plus a strong base. So HCl plus sodium hydroxide will form sodium chloride, and then the other ion combination produces water. One of the good ways to really illustrate what happens in this neutralization reaction is by looking at the complete ionic form, because our HCl completely dissociates, and so does our NaOH. So our 2 spectator ions here are going to be sodium and chloride, and the actual reacting components are going to be the proton and hydroxide. So the proton and hydroxide will combine to form water, as demonstrated by the net ionic equation. So anytime I'm reacting a strong acid with a strong base, we will always produce this same net ionic equation, because the ions both of our acid and our base completely dissociate. So anything attached to this proton or hydroxide is just going to be a spectator ion. However, this won't always be true if we're looking for a weak acid or a weak base. So let's go ahead and look at a good weak acid reacting with a strong base. Most notably, our good friend acetic acid reacting with sodium hydroxide. So again, like a precipitation reaction, we can treat this as an exchange of ions. So trading out a proton for a sodium. So in this case, we end up with sodium acetate and water. So let's go ahead and look at this in the complete ionic form. One of the big differences from the strong acid form is that acetic acid doesn't completely dissociate, while the sodium hydroxide will. And on the other end, the sodium acetate completely dissociates, while the water doesn't. So when we look at this, our only spectator ion is sodium. So this produces a net ionic equation of acetic acid plus hydroxide, producing acetate and water. And this is a very common sort of motif when we're looking at weak acid strong base reactions. Similarly, if I was reversing this and looking at a strong acid weak base, we'd expect to see a compound reacting with a proton to produce an ion and water. So again, this is a fairly cool way of looking at what's happening. If I have a weak acid reacting with a strong base, really what I'm doing is transferring a proton to a hydroxide ion. And this is really going to go a long way to defining our next type of definition of acids, which we're going to look at next time as we move on to Bronsted acids. Until then, take care.